Computers and time don't get along, and this relationship is going to blow up again on January 19th, 2038. You probably remember that there's a historic event known as the Y2K bug where this sort of rift between computers and time came to the forefront. Now, because a lot of the discourse was from people claiming that Y2K was going to cause planes to fall out of the sky, a lot of people remember it as this thing that was supposed to be a problem but wasn't. But it was a problem, and it was a problem that a lot of people worked pretty hard to fix. So with that problem, it was caused by computers storing the last two numbers of a year as the only numbers for that date, and the computer would just assume that it was the 20th century. And of course, on January 1st, 2000, it was now the 21st century, and computers would either crash upon trying to save the date, or save the date incorrectly and assume it was January 1st, 1900. We're going to have another problem like that on January 19th, 2038. And it's all about how computers store dates. So time is a fairly abstract concept. You can measure it in minutes, seconds, and hours, but time is also encompassing on the present, the future, as far into the future as you can possibly think, and the past, as far into the past as you can possibly think. So while it can be measured, there's not really anything to measure it against. And computers are strict logic machines. So computers solve this problem by creating a beginning of time, or what is known as the Unix epoch, which is January 1st, 1970. And to store dates, computers actually store the number of seconds that have passed since the January 1st, 1970. So for example, January 7th, 1970 would not be stored as January 7th, 1970. It would be stored as 604,800 seconds since January 1st, 1970. Now, in some systems, this is stored as what's known as a signed 32-bit integer. So a signed integer means that it can be positive or negative. So 0 is in the middle of what is available, and 32 bits is the amount of storage that is available to us. So a bit is a tiny piece of data that can be represented by two states, 0 or 1. So it's the same as having 32 columns of binary available to us, which is a finite number. So the problem that's going to happen on January 19th, 2038 is that the number of seconds that we have is going to run out. So to solve for the amount of seconds that we have since January 1st, 1970, we need to figure out 2 to the power of 31 minus 1, because we're including 0. The reason why we put 2 to the 31 and not 2 to the 32 is because we need to reserve one of those bits for the sign. So one of those bits is representative of whether it is a positive or negative number. So the answer to this is 2,142,483,648. Oh, it's an 8. And that seems like a lot of seconds. And it is, but we only have 18 years of it left. So if I was to divide this by 60 to get the number of minutes, and then divide it by 60 again to get the number of hours, divide it by 24 to get days, and then 365 to get years, I would get just over 68. The just over is January 19th, and the 68 years puts us at 2038. So when the computer gets here, it's going to crash. It's not going to let you store the date in that database system. It's going to say the number you're trying to store is too large. Well, now we get to the interesting part. How do we fix this? Well, we need to upgrade our system to use a 64-bit integer as opposed to a 32-bit integer. Now, a lot of our computer systems will already use that, and most of them will be using them. Most of them will be transitioned within the next 18 years. But that is something that has to happen. Now, you might be thinking that if we change to a 64-bit architecture, aren't we just prolonging the problem? Isn't it going to become a problem when we get to the end of what's available then? And the answer is no. And I'm going to explain that now. So let's figure out how many seconds would be available to us in a 64-bit architecture system. So let me change colors to blue here just to keep it interesting. We would therefore need 2 to the 63 minus 1. And this is not double this. Double this would be just 1 extra power. This is exponentially greater than this number here. The answer to this is actually 9.2 times 10 to the 18th power. That's 9 with 18 zeros next to it. That is a massive number. And if we divide this by 60, then by 60 again, then by 24 again, then by 365 again, we get 292,471,208,677 years. I don't think it's going to be a problem when we get to the year about 300 billion, because we certainly won't have computers then the way we know them now. In fact, the human race probably won't exist. To put it in perspective, a 64-bit string, a 64-bit integer has 100 times more years available to it than the 32-bit has seconds. And if you think about it this way, the Big Bang, the actual beginning of time, is estimated to be 4.6 billion years ago. This allows us to store dates in the positive direction up to about 300 billion years, and in the negative direction up to about 300 billion years. It's huge. Quickly, before I go, one other thing. This number is actually a Mersenne prime. Now, a Mersenne prime is a prime number that is 1 less than a power of 2, and of course that has a special name, because why wouldn't it? This number is a prime number, which is interesting. And another interesting thing is a Mersenne prime is actually the largest known prime number in existence. Another fun fact for you. So what do you do with this information? Well, if you're a computer scientist or you're building a web system or anything like that, make sure you're using 64-bit signed integers, because in 18 years it's going to become a problem.